Okay, so okay, let's continue. Just want to make sure that it's on. Okay. Okay, so we discussed gradient, semi-gradient TD and the solution that it would converge to, right? So let's look at an example. Like, let's go back to the 1000-state problem that we discussed before. Okay. Now here is the solution for gradient TD, like semi-gradient TD method for the same 1000-state problem with state aggregation. Okay. So we have 1000 states. You're grouping it into 10 different groups of 100 states each. Now you can see the quality difference between TD and Monte Carlo, right? So if you think about Monte Carlo, then, well, maybe I should have had both next to each other. So in the case of Monte Carlo, the star was very close to the true function, right? Like, but here the staircase is a little bit off from the true function, right? So this means that this is not the same solution that you would obtain from Monte Carlo. Now, one can actually extend this idea of gradient TD or semi-gradient TD. Okay. Semi-gradient is more formal, like, but I will just use gradient TD, like, so moving forward, like, but when I say gradient TD, it's really semi-gradient TD, okay? So we can extend this idea of gradient TD to n-step, gradient n-step TD, right? So, or n-step gradient TD, right? Like, so, like, it's very trivial extension, like, so we are not going to do that now. The algorithm is there in the book, I guess. Now, you see what happens for different values of n and different values of alpha. So this is similar to the graphs that we have seen before. And you can see, as you can see, always n is equal to 1 is the extreme case, like, which is basically one-step TD. When n is so large, it becomes Monte Carlo, okay? And you see that something in between actually has a good, performance. Is that clear? Okay, so now I want to go back to this question that was asked before, right? Like, so, like, if it is a linear model, then why do we do gradient descent? Like, can't we find efficient closed form solution? Okay, okay, this out. Okay, so, and towards the end of the discussion, we also saw that the fixed point or the solution for linear gradient TD is something that we can compute, which we computed recently, right? Like, so, just to recap, the WTD or the TD solution is given by A inverse of B, right? Where A is expected value of xt minus gamma xt plus 1 transpose, and B is given by expected value of RT plus 1 xt, right? Now, if I know this is the solution that I'm going to get, then why do I compute this solution iteratively? Why don't I directly estimate this solution from the data, right? So in some sense, if you do iterative process that we discussed before, it's kind of wasting the data because you have to iterate and you have to do it a lot of time steps, like, before you converge to the solution, okay? A smarter way is to actually compute estimates of A and B. And then directly computing this fixed point. Is it fine? So there is an algorithm which does this, okay? So it's called least squares TD, okay, or LSTD. Okay, so the idea of LSTD is really simple. Like, given experiences, instead of trying to estimate, like, instead of trying to do the iterative process to reach to the fixed point, I'm going to directly compute the estimates of AT and BT. Okay. A and B. We are going to call that as AT and BT. Okay. So AT, an estimate, is going to be summation over k is equal to 0 to t minus 1 xk minus gamma of x k plus 1 transpose plus some epsilon I. Okay, and b hat of t is going to be summation k is equal to 0 to t minus 1 or k plus 1 of xk. Is that clear? Where this I is the identity matrix and this epsilon, which is greater than 0, is a small number, non-negative number, just to make sure that when you compute this A inverse T, right? Like imagine, like remember that your W is given by this estimate inverse B estimate of B, right? So when you do the inverse, like you should make sure that the inverse exists. One simple way to do that is to just add this small positive value. Is that clear? So if you remember ridge regression, this is what we did in ridge regression. Okay, now this is going to be the most efficient way of doing gradient TD. Okay, so if you want to do TD with linear function approximation, this is probably the most efficient way. But there are some trade-offs between the iterative solution and this solution. Okay, but before that, do I need to? So we are trying to estimate expected values of A and B, right? But I'm just summing things here. Like, do I need to average instead of sum? Shouldn't I be averaging these examples so that I get an estimate expected value instead of summing? So in this case, if you think about how we are using these estimates, right? So you have A inverse times B. So even if you're averaging both by n, so that's going to get cancelled. So since you're having the averaging effect in both numerator and the denominator, it is okay. You don't need to divide it by t. Is that clear? Okay. So now, how complex is this algorithm LSTD? Okay. So we have semi-gradient TD, which is the algorithm that we saw before break, right? And now we have LSTD. So semi-gradient TD is an iterative algorithm. Okay, well, LST is also a bit iterative. Okay, so but this is iterative in the sense an iterative algorithm trying to estimate the value functions. Okay, estimating value function. But this algorithm is an iterative algorithm, but estimating A and B. Okay, now what are the computational complexities of these two algorithms? Right. So if you think about semi-gradient TD, the computational complexity is just order D. It's a linear complexity algorithm because it is just one update equation, which is based on the number of features, right? However, if you do LSTD, okay, now in the case of LSTD, first of all, it looks like the computation is actually increasing for every time step because it's a summation, running summation, right? But in the very first week, we have seen how to implement these kind of running sums efficiently, with constant computation, right? So in theory, we can actually, well, even in practice, we can actually convert this into some constant computation step by incrementally computing this sum, right? However, within this computation, right, you see this particular part. It's a vector. There are two vectors, but you're doing an outer product of these two vectors to construct a matrix, right? Essentially, it's a matrix operation, which means just for computing AT, you need order D square, okay, for computing AT. Yeah?
And then we have to compute the inverse.
Yes, that's the next point. Good point. So, and also you need to compute A inverse, right? So can someone tell me what is the computational complexity of computing inverses of matrices?
Like D cube.
D cube, right? So it's actually order D cube. So essentially, we want to replace an order D algorithm with an order D cube algorithm. Okay. Now, why would one do that, right? Like, so it looks like the per step computation is high here, right? Like, so, but there are a couple of, yeah.
Is order D correct? Because I think you need to also take into account how many times
Yeah,
you're putting up.
yeah, that's okay, that's what I was about to come. So now this is per step computational complexity, okay? But in the case of gradient TD, you have to run it for a long time. On the other hand, this LSTD is going to converge much faster. So it is like you do more computation per time step, but then you converge faster, okay? Also, there are ways to make this LSTD algorithm more efficient, okay? I will explain it, but I will not get into the details of it because it's more of like a matrix optimization course than a machine learning or reinforcement learning course. Like, so in this case, there is an efficient way to do this matrix inverse with just order D square, okay? It is because of the fact that the matrix that you are trying to inverse, right? So that matrix is sum of outer products, right? So if you have a matrix which is a sum of outer products, then there exists an efficient incremental algorithm which is only order D square complexity. So the algorithm is something like this, okay? I will not try to explain what the algorithm is. So A inverse, incrementally computing A inverse is basically AT minus 1 plus xt minus 1 xt minus 1 minus gamma times xt transpose the whole inverse. Okay, so you are just you'll be applying recursion here, like, and you will get a final solution which is going to be something like this. Okay, minus at minus 1 inverse xt minus 1 xt minus 1 gamma xt transpose at minus 1 inverse divided by 1 plus xt minus 1 gamma xt transpose at minus 1 inverse xt minus 1. Okay, it looks like a very complex formula. You don't need to understand what is going on inside, okay? So this is a standard formula, like it has a name, which is Sherman-Morrison formula, okay? Now, the initial A0 is going to be just epsilon I. So you start initializing your inverse, say your A matrix with epsilon I, okay? And you can compute your inverse more efficiently by just using this incremental formula, okay? This is order D squared because you can go home and verify there is no matrix operation here. So all the operations here are like either vector or vector matrix, okay? So it's an order D square operation for inverting the matrix, okay? Now, overall, the computation complexity of LSTD is just order D square per time step when compared to order D for gradient TD. Is that fine? Now, one might think there is additional advantage for using LSTD because LSTD doesn't have the learning rate or step size, right? So in the case of gradient TD, there is a step size alpha. So depending on how you choose your alpha, you're going to have different learning dynamics. You can diverge, you can converge faster, you can converge slower, right? Like you don't have that issue with LSTD. But there's a small catch. So instead of hyperparameter alpha, you have hyperparameter epsilon, okay? So we often think that epsilon is just for numerical stability, okay? But it has significant impact in the learning speed. So if your epsilon is too small or too high, it is going to have different effects in how fast this LSTD algorithm converge. Okay, so there is actually a hyperparameter here. And also there is another advantage of having alpha. Can someone tell me what is the advantage of using alpha, like in gradient, in general in learning?
We can have a bigger value and start putting it.
Oh, it's not, it's about, no, I'm not talking about the convergence. Like, so what is the effect of alpha? Like,
The learning rate?
sorry?
The learning rate?
Yeah, the learning rate. Like what is the effect of alpha, like other than just taking a step towards the gradient, right?
You can forget the previous.
Yes. So you can, like, if you think about non-stationary setting that we have seen in Bandit, right? Like, so if you have a constant alpha, then you're exponentially decaying the weight of the previous experience, right? So alpha has this effect of forgetting the past, which is kind of essential whenever your policy is changing or when you're in a non-stationary environment and so on, okay? Even in a stationary environment, like when you do generalized policy iteration, your policy is constantly changing. So you don't want to give too much weight to the past, right? So which means LSTD is at a disadvantage because it cannot forget the past. It is just integrating everything. Now, there are many variations of LSTD, like where you can try to bring in the forgetting aspect and so on. Okay, so but probably we will not talk about that in this course. Like, so if you're more interested about LSTD, like you can read more about it. But here is the algorithm as a summary. So you basically start with some estimate for A inverse, and you start with some B, and every time step you take an action, okay, and you just compute this update equation, which looks complex, but it is very easy to implement, and you continue this, and you're going to converge to a policy. Sorry, you're going to converge to the value function. Is that clear? Any questions so far? Any questions? So we are really in an uncharted territory now because I don't have notes. Okay. Okay, so, okay, I think I will stop my discussion on this kind of gradient methods here and go back to this another fundamental problem, which I said we will talk about later. So if you think about how we started constructing the features of the state, right? So like I told you that features are given. So who gives these features? Like, so we are the designers, right? So we have to design these features. Now, let's talk about representation of states. Okay. Now, given a representation of the state, we know how to do function approximation. So that part is done. Okay. Now let's talk about representation of states themselves. Okay. So as I mentioned before, like depending on what problem you are interested in, like so you're going to construct different state representations. Like so, for example, this is the place where you can add your prior knowledge. Like for example, let's say you're playing a video game. Okay, like you're designing an agent to play video game. Now the objects in the game matter, right? So you can have one feature representing, whether there is an enemy in the screen. You can have another feature, which is basically the score that you see for the game. You could have another feature which says, what is your current XY position, like a couple of features. And you can have another feature which says how far you are from a bridge or a target or something. You can construct a lot of these features manually, okay, and feed that as input to your linear model. Okay. Now, when you have linear models, okay, which is essentially just W transpose X, right? So the big disadvantage of linear models is there is no interaction between these between the features. Okay. So I'll point to the example given in the book, which is the task of pole balancing. Okay. Let's say I'm not sure if you have seen pole balancing before in any of the examples, but the task is really simple. Like you have a pole, okay, which you want to balance. Like, so it is always going to move. Like the gravity is always going to bring it down, but your goal is to change the velocity in such a way that, like, velocity and direction in such a way that, like, it is always balanced. Okay. Now, in this case, there are two features that we care about. Okay, and they are basically okay. So there are two features that we care about here. Like one is the angle of the pole, okay, and the next is angular velocity. So given angle and angular velocity, like you decide how to move further, okay? Now, it is very, very important that you consider these two features together. Why? Because having a very high angular velocity, when the angle is large, is a bad idea. Like if you have very high velocity when you are in a proper balance, then you're going to fall down, okay? On the other hand, it is actually very important that you have high angular velocity when you are like almost close to the floor, right? Like so, like if your pole is here, to bring it up, you need high angular velocity. But if your pole is here already, a high angular velocity is actually a bad thing to have. Okay. Now, the value of the state cannot be measured by just considering these two things individually. If you have a linear method, which is just taking these two things individually, it is going to have a very hard time solving this task. This is a simple task. There are only two features, very simple to do, but extremely hard for linear methods if you don't have model the interaction. Okay. Now, how can we avoid this problem? Any answers? Yeah.
Merge them into one feature.
Yeah, you can construct another feature which is kind of considering the interactions between them, right? So now there are many ways in which you can improve this. Okay, so like if you are also in the ML course, like you have already seen like different basis functions, right? Like so even if you're not in the ML course, like we are going to see some examples today. Okay, so the first way to construct is exactly what he mentioned, which is the idea of using polynomials. Okay, so where let us say I have two features, S1 and S2. Okay, I can consider S1 as one feature, S2 as another feature, S1 multiplied by S2 as another feature. Now this considers the interactions, right? I can also have another, normally we will also have another feature, just one, to give more expressivity to the model. Okay, so this could be one way to represent like my features, then pass it to the linear model. Now there is already this interaction which is going to help the linear model, right? Now you can expand this as many times as you want. You can have one, S1, S2, S1 square, S2 square, plus, sorry, S1, S2. So, okay, so this is 2-degree polynomial. 2 or 3, I always confuse. So it's more than 1 degree at least. Okay, so so now you can expand this to any n-degree polynomial. Like you can have even more complex interactions like S1 square S2, S2 square S1, and so on. And if you have 10 features, you can have all possible interactions of these 10 features. So now you can basically construct all these interactions and pass this polynomial function or polynomial representation as input to your linear model, and you're going to do well. Is that clear? Now, as you can imagine, this is really an inefficient way of doing things. If you have more features, for example, you have 100 features, how many possible pair interactions are there? There are just so many pairs and so many triples and so many quadruples, right? Like so the number of features are going to explode if you do this kind of polynomial feature representation. So it's very naive. Like I'm just teaching it so that you know that you can do that. So we're going to do a slightly better feature construction, okay, which is the idea of coarse coding. Okay, so coarse coding is a really simple idea. So imagine you have your state represented in a continuous space, continuous 2D space. Okay, so for example, your grid world, right? Like so when you have a grid world, it is a 2D space where you can move around, right? So if you have such a continuous 2D space, now I can actually construct, okay, some features which are basically circles. And maybe I'll give you an example. So in this case, you can see each circle, okay, this is my space. Each circle you are seeing is actually a feature, okay? Now, for example, if this is my state that I'm considering, okay, I will just check whatever circles are there in this particular state. Okay, so this particular state includes this circle and this circle, right? So I'm going to put 1 for those circles, circular features, and 0 for the rest. Is that clear? So we are kind of coarse coding. So that's why it's called coarse coding. So there is one difference between this and state aggregation. Okay, in the case of state aggregation, you would normally group things together, and everything in this is considered to be one state, right? But in the case of coarse coding, you see that there is already some sharing happening because, for example, like let's take one circle. Okay, let's consider this circle. Maybe it's easier if I highlight. Let's consider this particular circle. Okay. Now this circle actually shares knowledge with this circle, this circle, this circle, this circle. It shares knowledge with various circles. Like for example, you have a state here, it is going to update 2 circles. You have a state here, it is going to update 2 other circles. You have a state here, it is going to update 2 other circles. You have a state here, it is going to update 3 circles, right? So now in some sense, whenever you are updating one particular state, you are also updating some neighboring states, and the notion of neighbors is decided by this circle. Okay. Now to construct these kind of features, like so what information do we need? What are the hyperparameters here? So we need to consider how many circles to use, right? Like the number of circles or number of features. Anything else? The diameter of the circle, right? Like so how big or small the circle is going to be. Now how big or smaller the circle is going to be, you are going to have different types of generalization. Okay, so for example, so here you see with smaller circle, this particular data point or state is only affecting 1, 2, 3 circles, right? But with larger diameter, just this one state can update 4 or 5 circle features, right? So now depending on how small or large is your circle, like you're going to have different types of generalization. This is narrow generalization. This is very broad generalization. Okay. Now you have to be careful. Just because you want broad generalization, you should not go for bigger and bigger circles. Why? Can I just increase the size of the circle as much as I wish? Because it is going to give me more generalization.
No circles.
Sorry?
No, because then it's like no circles. Every feature is always.
Yeah, so there is a trade-off, right? Like so, as you get more bigger and bigger, you think you are generalizing to all the states, but then like you are having a very crude approximation. It is like considering all states to be one state. So that is really bad idea, right? So we don't know what is the right level of approximation. So it's a really hyperparameter. You try different diameters and see what happens. Okay. Now, nobody forced us to use circles here. Like, okay, so you can actually change the shape. You could have some sort of ellipses. Like you could just change the orientations of these circles a bit. Then you will have asymmetric generalization. Okay. Now, this is more like a art in the sense you try different things and like we don't know what works. Like you try a bunch of things and you see something is working. Okay. Next week we will talk about how to do better than this. So this is a lot of manual work, right? Like so you have to try different possible radius. You have to try different number of features, right? Like so it looks like magic, like to find the right configuration. So we're going to see how to do better than this in the next week. Okay, but for now let's stick to this coarse coding. Okay, now depending on how narrow or general, like broad your features, right? Like you're going to have different types of solutions. So here is an example where my goal is actually to estimate this blue function. Okay, this is the function I want to estimate, and I'm using coarse coding here. This is a simple 1D function, right? So what do I mean by circles in 1D? So it is just intervals, right? Like so, I can take this 1D line. I'll have this as one feature, this as another feature, this is another feature. Okay, instead of circles, I'm going to have like intervals with radius. Okay, now this is what happens when you have narrow features. This is when you have broad features. You can see that depending on how you choose your features, like the intricacies of your final solutions are going to be a little bit different. Like you can see that this is like a little bit wiggly. This is like more flat. However, like you reach an approximately good final solution, which just means that this is actually a robust idea. Like you don't need to worry too much. You're going to reach a good, like a reasonable solution. Is that clear? Any questions about course coding? Any questions in the chat? Okay, so now there is actually a more efficient version of course coding. Okay, so which is called tile coding. Okay, so there is a question in the chat. Is it widely used in practice? Okay, so that is where I'm coming. So course coding is a bit difficult to implement. Okay, well, like there is an efficient version of course coding which is called tile coding. So tile coding is widely used in practice when you have linear models. Okay, but of course, like we will see later that linear models are not optimal for all the problems. Like for really complex problems, you have to go for nonlinear models. But if your problem is simple enough that you can use linear models, then using tile coding with linear model for function approximation is like one of the default choices that people use. Okay, so let's talk about tile coding. So tile coding is really some modifications to course coding so that it becomes more efficient to implement. Okay, so in the case of tile coding, like let's say this is my space of states. Okay, so tile coding is going to have tiles or partitions of this space. Okay, now for example, like I could divide things like this. Okay, now this is my first tile, this is my second tile, this is my third tile, 4, 5, 6, 7, 8. 15, 16. Okay, so this particular tiling has 16 tiles. Whenever a state occurs here, that tile is going to have value of 1 and the other tiles are going to have value of 0. Okay, now just by this definition, this looks like a state aggregation, right? So there is not a lot of benefit. So how do I combine this idea with course coding? Any idea? I want to share knowledge. I don't want knowledge to be disjointed. Okay, so he raised first. Yeah.
You can weight it on you like according to the proximity of the type.
Sorry, can you please repeat?
You can give the highest value to the, for example, the type 4, and then a smaller value to 3 and 8, so on.
Okay, so you kind of give some extra values to others instead of making it 0. Okay, good idea. You?
More values for neighboring tiles.
Okay, all are same solution. Okay, so all of you are saying give some values for neighboring solutions.
Overlap the tiles.
Okay, so that is a second class of solution, which is what I was about to talk about. Like so, like a simpler. Okay, so the thing is, the problem with like giving values to the neighbors is like it's a good idea. I'm sure there might be some paper which is doing what you are suggesting. I'm not sure if that is more efficient than what I'm going to talk now. Maybe let me tell my solution, then we can talk about which is more efficient. Okay. So the second solution that like he suggested, which is what I was thinking, is like basically having more tilings. Okay. Now, instead of just having this one type of tiling, like how about I have another tiling, which is looking something like this. Okay, it looks ugly, but you get the idea, right? Like so now, this has its own tile features. Now I can have as many tiles as I want, tilings as I want. Okay, so maybe I'll go to the neat picture. So here you see that there are 4 tilings. Okay, blue, orange, red, and green tilings. Okay, now if you consider this particular white point, which is my state. Okay, very bad color choice. Maybe let me do black. Okay, so if you consider this particular white point, now that is going to be represented by different tiles in different tilings. Okay, so the whole thing is called tiling, and it has individual tiles. So it is going to be represented by 4 tiles or 4 features from different tilings. Okay, now you can easily see that I just move a little bit here. It is going to be represented by 4 other types of tilings, right? So now the tile features between tilings share some knowledge, which means you are learning from one state to another state. Yeah.
Isn't this the same as using smaller tiles and like each small tile have a different like I can see that like superposing these 4 big tilings, it creates a lot of small tiles.
Oh yeah, a lot of small tiles, but then like if you go for the small tile solution, right, like then you're still not sharing knowledge. Like for example, take the same grid. If you go for small tiles, right? So if you go for small tiles, like you are still not sharing knowledge from here to here. But this is more efficient way of doing that. Like you're sharing knowledge from one place to another. Is that clear? So now here is a solution for the 1000 state problem that we have seen, right? So this is state aggregation solution, okay? And this is tile coding solution with 50 different tilings. So you can see that when you share knowledge, you are learning faster. So, well, you get to better value and also converge faster. Question?
How do we know how many tiles to?
That is a good question. So, well, how many tiles to use? Like, what is the size of the tile, right? So these are hyperparameters. Okay, so you have to try different number of tiles, and for different values, you're going to get different performance. Okay.
So how is it different from the previous circle?
Oh, it is not very different. It is just that it is very easy to implement this when compared to coarse coding. Like with coarse coding, like you really need to consider all possible circles, and you have to do a lot of computation. When you start implementing, you will see that it is very hard to even think about how to implement coarse coding. But in the case of tiling, it is very easy. And even in terms of inference, right? Like, so when you want to use this model, so at any point of time, you're going to have certain things activated, certain things not activated. And it is just easier to implement. So, but tile coding is a form of coarse coding. So it's not a different algorithm.
So in the previous slide, there were something like a slash features for each tiles. Like
tiles are just called features.
No, I mean, does each layer correspond to some kind of a specific feature?
No. If you have 4 tilings, each having 25 tiles, then you have 100 features. Okay. That clear?
And the order remains the same within all tiles?
Yes, but the order really doesn't matter, right? Like it's a linear model. So you're not doing a connet or anything complex. Like you're just doing a linear model. You construct these 100 features and then you pass it to this linear model. So its order doesn't matter. Okay, now depending on how you place your tiles, right? So you're going to get different types of generalizations. Okay, it's here. So you can see that if you place your tiles like this, very fine next to next, okay? So depending on how you place it, you're going to generalize in different ways. Like you see that if you have like uniform offsets, then you often generalize only in one direction. In this case, it is generalizing in this direction, right? So often when you construct your tiles, you should try to construct it as asymmetric as possible, like this, okay? So that you generalize much broader. Is that clear? Any questions about tile coding? Any questions about tile coding so far? Okay, so I want to quickly go through the control then. Okay, so far we have been doing prediction, just prediction, right? Like our interest is control. Now how to do control, right? Like so on policy control with approximation. Okay, well, as we progress, you can see that I go faster over these things because it is really a routine process. You do prediction first, then you do control, and then you talk about on policy and off policy in control, right? Like so we are essentially, we are not we are not designing new algorithms here. We are only extending the old algorithms. That's why I'm going a little bit faster. But please go back and read the textbook if you think this is too fast. Now, how do we convert all these gradient methods to control, right? Like, so it's really simple. Like the first step, as usual, is to change from state values to action values, right? Now, my update equation, like for example, in the case of general update equation is going to look something like this. So Wt plus 1 is equal to Wt plus alpha times Ut minus, instead of the state value, I have a Q function approximation. Okay, so Q of STAT given Wt. Okay, then dou by dou W of Q hat of STAT given Wt. Is that clear? So it's the same equation. The only difference is instead of state value, I have Q values. Right? Like for example, like if you want to do one-step SARSA, so which is a on-policy control algorithm, right? So if you want to do one-step SARSA, it's going to look something like this. Wt plus 1 is equal to Wt plus alpha times RT plus 1 plus gamma times Q of ST plus 1 AT plus 1 Wt, okay, minus Q of ST AT given Wt, the whole thing multiplied by dou by dou W of Q hat of ST AT given Wt. Is that clear? So there is really nothing to discuss much here. Like so, like you can, it's very trivial to extend the prediction to control. Like so, here is the semi-gradient SARSA. Okay, for it, see that we are actually estimating the action values, and we are learning the policy here. Like this is not a prediction algorithm; this is a control algorithm. So it looks very similar to SARSA, right? Except for the fact that we have this. Sorry. Except for the fact that we have these gradient updates, right? So now let us see how this semi-gradient SARSA would work. Okay. Now for this, like we are going to use the standard mountain car example. I'm not sure if you have seen mountain car before, right? I don't think so. So this is a classical control task. Probably you will use this in your future assignment. So the task is simple. Okay. So the task is you have you have a car. Okay, and it's kind of an underpowered car. Okay, so it's an underpowered car, and the goal is here. So you need to reach the goal, but the gravity is much more stronger than the power of the car. So you will always be pulled down. Okay, now how would you solve this problem? Yeah, so you develop momentum, right? So like if you want to cross here, like against gravity, you go here, so you develop momentum, you try to go, you do this, you do this, you do this, you do this, right? Now, as you can imagine, this is a really hard problem for reinforcement learning agents. Why? Because this policy requires you to actually first go to a low value state before you go to the high value state, right? Like it is very unintuitive, like so. Like you have to first go against your goal so that you develop momentum and go to the goal, right? Like so, it's a hard problem. It is notoriously difficult, like even for sometimes for like the modern reinforcement learning algorithms. Okay, so now how to solve this problem? Like so we are going to do semi-gradient SARSA. Okay, so here you can see that. So in this case, I'm estimating steps per episode in log scale. Okay, so when I say steps per episode, it's basically you will be getting -1 throughout until you reach the goal. Okay, so the reward is essentially like how fast you reach the goal. So if the number of steps per episode decreases, then you are learning. Okay, for different values of alpha, you see this is how the semi-gradient SARSA performs. Okay, in this case, like we are using tile coding, and we are basically doing epsilon greedy with SARSA. Is that clear? So now you can actually extend this to, like, for example, n-step semi-gradient SARSA. Okay, so I will not talk about it, but here is the algorithm. Like it is really semi-gradient SARSA. It is really n-step SARSA. You take n-step SARSA and just update this part, so that you're doing function approximation instead of the normal n-step SARSA. Okay. Now for the same mountain car task, right? So here is how n-step semi-gradient SARSA would look like. So this is n is equal to 1, this is n is equal to 8, and as you can see, always like larger value of n helps, and you cannot keep increasing the value of n. Like you can see that n is equal to 4 seems to be a good number than other n's. Okay, so well, I will stop here, like, and quickly summarize what we have seen so far. Okay, so we talked about value function approximation. Right? So which is basically this idea that coming up with this tabular value function is always coming up with this tabular value function is hard. So instead, can I just approximate it by using some value function approximator, which takes x of s as input and gives me the value or estimate of v pi of s. Right? Now, there are many components here which we discussed today. Like, first of all, like, what is this value function approximator? Like, so we have seen only one such approximator today, which is the linear model. So which is basically W transpose X of S, right? And we also discussed what should be the objective function here. So the objective function for this approximator is the VE of bar, right? So the sample average of this is going to be like whatever V pi of S minus the V of X or X of S given W, the whole square, right? So we discussed the objective, and we also discussed how to represent the features. Like, so the features could be represented just simple raw features or polynomial interactions or tile coding or coarse coding and so on, right? Like, so then we talked about like how to integrate such a system with Monte Carlo or TD, right? Like, so if you integrate this with Monte Carlo, you get gradient Monte Carlo methods. If you integrate this with TD, you get semi-gradient TD methods. Now, you can take this gradient Monte Carlo and semi-gradient TD prediction, add control to it, you get the control variance of it, right? Like, so we did not talk about how to do control, Monte Carlo control with policy, with value function approximation, but maybe I can just leave that as an exercise. Think about how to construct an algorithm which is doing gradient Monte Carlo control. Okay, so it's very simple, but we did see gradient TD control, like which is SARSA and n-step SARSA. So we will stop here. So next week we are going to talk about how to do function approximation with off-policy methods, which is a big challenge by itself. Okay, and we are also going to talk about the challenges in doing off-policy learning plus function approximation. Okay, you'll see that it is really difficult. There is a lot of divergence issues, like you cannot converge and so on. And finally, we will talk about how to do nonlinear function approximations, like using deep neural networks, and like what are the challenges that you would face when you have nonlinear function approximators. So that is after the break, like after the study break. So we will stop here, and I know a lot of you wanted to ask me questions during the break. I was preparing, so now you can come and ask your questions. This is my office hour. Thank you.